Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Joris Verbiest. He received his PhD in 2009 from the Swinburne University of Technology, and since 2022 he is the project manager of the International Pulsar-Timing Array at the Florida Space Institute and research professor at the University of Central Florida. Thank you very much, Joris, for agreeing to give this talk. The stage is yours.
Thank you, Tobin. And thank you all very much for inviting me here and for adjusting your seminar slot to accommodate my time zone. It really is much appreciated. So yes, today I'll be talking about gravitational wave detection with pulsars, otherwise known as pulsar timing arrays. I'll be trying to give you a bit of a historical overview, not too much of that, but also a lot of technical background as to how this really works and what the challenges are, because as I'll show, we are getting into an interesting regime. If you looked at a pulsar timing array talk about 10 years ago, there's a very good chance you would have seen a cartoon like this, where you have a bunch of pulsars spread around the Earth. You have this traditional space-time mesh, which is sort of undulating, and therefore is distorting the paths between the pulsar and the pulsars and the Earth. And so because of these different distortions, we can detect gravitational waves. This was a cartoon that's been shown very much throughout the history of PTAs. But interestingly, in the last couple of years, the cartoon that you've been, or the image that has been shown much more often is this one. And so a few of these things are still recognizable, and the same, you still have that space-time metric, obviously. You still have the millisecond pulsars, and I believe you can see my cursor, right?
Yes, we can see it.
Excellent, thank you. But you can also see that the focus has shifted significantly in the sense that now we actually have in the background the sources of the gravitational waves as well. There's also, this is obviously a more professional artist's rendering, so maybe there's an illustration of the increasing funding over the last 20 years. But more interestingly is the fact that indeed we are, as this project is evolving, we are getting closer to actually detecting gravitational waves and doing astrophysics with it. And so it's that evolution really that I'll try to illustrate. But also, as mentioned, I'll try to highlight some of the pitfalls, because as we go towards actual gravitational wave astrophysics, it becomes more important that we are aware of what can go wrong, because we don't want to make mistakes in such high impact science, obviously. So to briefly lay out sort of the map of the coming hour or so, I'll give a very brief introduction to pulsars, just to situate where we are in terms of the sources that we use for this experiment. Then I'll go into pulsar timing arrays, and particularly how that works, along with some of the more technical details. And then about half of the talk, or a bit more than half, would be taken up by progress and state of the art, where I'll explain exactly where we stand with all these facets of the project and how that affects our sensitivity, how far or how close we are to a gravitational wave detection, and what you may want to expect or keep your eyes open for in the next 6 to 12 months, most likely. There'll be a very brief summary at the end for takeaway messages. In case you fall asleep, the last slide will save you anyway. So very briefly, pulsars are neutron stars, so they're compact leftovers of supermassive stars that went supernova. Because they are very compact and because of conservation of angular momentum, they spin very rapidly. This animation has been slowed down tremendously. The real objects spin much, much faster, and we'll get into that in a moment. But also, because they've been compacted so much compared to their progenitor star, the magnetic field has also been compressed, and so they have extremely strong magnetic fields. Because of the strong magnetic fields, you get some kind of curvature radiation at the magnetic poles, and because the magnetic axis and the spin axis are offset, you get this lighthouse effect, where a beam of radiation is swept around in space, and if that hits the Earth during its rotation, we perceive this pulsar as a series of pulses. That series of pulses is what enables us to time it. That means to measure the arrival time of the pulses and see how they evolve in time. And that's really the fundamental property that we'll be exploiting here. This is, if you like, the Hertzsprung-Russell diagram for pulsars. It is not show color or magnitude. What it does show is spin period on the x-axis and spin period derivative, so the slowdown of the spin, because of course it loses energy as it goes on the y-axis. And so I could give you a whole lecture on this particular diagram, but the two main things that should stand out straight away, are the big, what we call the main island here of black points, sort of in the middle to top right. Those are what we call the slow or the normal pulsars. They spin with spin periods of a few hundreds of milliseconds down to up to a few seconds. I think the record holder is about 24 seconds at this point. Because they're so slow in their rotation, and because they have certain properties, for example, they're not as stable as you would like them to be, these are typically not the pulsars we use for pulsar timing arrays. The second thing that stands out is the smaller island in the bottom left, which has some kind of tenuous bridge with the main island as well. That one is pulsars that have spin periods of a few milliseconds. And the vast majority of these are in binary, so they're red points because they have a binary companion. That's most likely an evolutionary cause behind that, and it doesn't really affect our timing so much. So it's mostly the spin period here that causes the timing of these to be really precise. The fact that the spin down is so slow, that means they don't really spin down appreciably. In fact, they don't even move on this diagram in a Hubble time. That also makes them very stable objects, and therefore you can predict their pulse arrival times, their spin period, really precisely as you go. So these are the main classes: the normal or slow pulsars, the millisecond pulsars, and so that is about 10% of the total pulsar population, and those are the ones that PTAs are currently aimed at. That tenuous bridge is the double neutron stars. They're really interesting for tests of gravitational physics, and so for relativistic effects in tight, massive binary systems. So they definitely have a gravitational interest there, but because their spin period is about a factor of 10 slower, they're not quite as precisely timed. So typically they're not targets for PTAs. Magnetars I will completely ignore in this talk. That's a whole different topic. So the way in which we time these pulsars is sort of illustrated here. It's basically just a model fitting exercise. You have on the top here in the diagram, you have your observed pulses, and they vary a bit from one to the next. Their amplitude obviously gets a bit modulated by interstellar scintillation. Their shape is also a bit variable on short time scales due to instabilities in the pulsar magnetosphere. But on average, these pulses are stable and repeatable. Because they're stable and repeatable, we can make what we call a template, which is basically the ideal pulse shape without any noise. Just this is what the pulse shape should look like. And by comparing your template pulse with your observed pulse, you can get an arrival time. And in fact, you can see how the difference between the template and the observation changes in time, and that's the residual. Now, this is a bit of a caricature animation here. We could go in a lot more detail, but for the purpose of understanding what we're doing, it's basically this, that you have your actual arrival time, that is when the pulses really arrive. You have the modeled arrival time, that's when you expect them to arrive. And then the difference between those is the timing residual. And the timing residual, therefore, contains all of the information, all of the physics that happens in real that has not been modeled. And so that's where we're going to find and learn our new science. These modeled arrival times, that of course derive from a mathematical model. And here at the bottom, this is not the exact timing model. It's just to give you an indication of the main things that play there. Of course, you've got the spin frequency, the spin down, which we mentioned. Everything is dependent on time, obviously. These are position vectors between the pulsar and the Earth and the solar system barycenter. This is the velocity of the pulsar, so the proper motion, effectively. And this is how these multiple things interact, how the Earth's orbit interacts with the pulsar position and motion, etc. There's a lot more terms that I'm not gonna bore you with, because you can read up on them if you like, but mostly those refer to binary effects. And so because we look at millisecond pulsars, and because millisecond pulsars are almost all in binary systems, there's a lot more model fitting to be done there, and some of these terms get quite complex. One term that we will come back to in detail is this one here. D is just the constant, F is the observing frequency, and NE, well, capital D is a constant, lowercase d is the distance to the pulsar. NE is the free electron content. So this is what we call the dispersion term, because the interstellar space to a large degree is filled with free electrons, and free electrons do interact with radio waves, or with any electromagnetic waves, but particularly with radio waves because they have such low energy. And so as our pulses, our radio waves from the pulsars travel to Earth, they get the group velocity of these waves gets affected by the by the ionized medium in between, and as a consequence, the arrival times are affected as well. So the more free electrons we have between us and the pulsar, the more the pulses get delayed. Interestingly, this is frequency-dependent effect. That means low-frequency observations get delayed more than high-frequency observations. That's kind of nice because it means we get a way to measure this effect. And that's critical because, as we'll see, this electron density is not constant, primarily because the pulsar is moving typically at a pretty high velocity. I think the average or median velocity of pulsars is on the order of 100 kilometers per second. The line of sight to the pulsar actually moves through the galaxy as our experiment evolves, and as a consequence, this integrated electron density changes, and therefore this delay term changes. And that will turn out to be one of the main headaches that we have in this whole experiment. Now, I said the timing residual contains all the information that we don't know yet. Well, just to give you an idea of what that looks like, here in the top left corner is a real, somewhat outdated data set from the Parkes pulsar-timing array. That's the Australian experiment. There's a lot in here to dig out. You immediately notice that some observations have huge error bars, others have very small error bars. There's a lot of reasons why that could be. It could be because the pulsar happens to be faint that day. It could be because we observed with a different instrument at a different frequency, etc. You can also see some of these error bars are obviously underestimated. There's, again, a whole host of different reasons why that might be the case, and these are active areas of research. But on the whole, there's no clear structure in this top left plot. The fact that there's no structure there, no discernible structure, basically that it is white noise, as we call it, that indicates that a timing model here has been optimized. If the timing model had not been optimized, we typically would see one of these other structures. These are very deterministic structures. Here we have a parabola in the top right corner. That's the signature, as it were, of the spin period and the spin down being wrong. And so by optimizing the period and the spin down, we can get rid of that parabola and revert back to the top left plot. The other examples here in the bottom left corner is an error in position, and so you get an annual sine wave because of that. And in the bottom right corner, you have an error in the proper motion of the pulsar, which means that you effectively have an error in position that grows linearly in time. That's why it's again an annual sine wave with an amplitude that increases linearly. And so by inspecting your timing residuals, you can basically figure out which timing model parameters are wrong. But even when you fix all that, you improve your timing model parameters up to the point where you don't have those structures, then there's still a lot hidden in there. And that is now really the challenge of PTAs, to try and figure out everything that is still wrong and missing in that top left plot here. So just to recap, all the knowledge that we have, everything that we know and can predict is in the timing formula. Everything that we have not correctly modeled yet is in the residuals. And there's a whole bunch of unmodeled effects that would be in these residuals. Here on the right, we have, again, it's slightly outdated, but not terribly much. I'll show you something about the timescales of PTA analyses, and a few years delay is not unheard of. So this data set goes until somewhere in the start of 2024. This is from the European pulsar-timing array this time. And you can see a variety of things. In fact, every different color is a different observing frequency. And you can see some frequencies, like the light blue one, is extremely tight. This is because it's a highly sensitive observation. And so the white noise, the radiometer noise, or the measurement error, if you like, is minimized. And that's why it's so incredibly tight. Once you zoom in, of course, you will see that there's more variation there still. Other frequencies, like the light green one, that's a slightly lower frequency with a narrower bandwidth. And so that's less precise, and therefore you have more measurement error. And then the white and the purple points, those are really interesting because they actually spread out at particular times, which are exactly separated by 1 year. That is due to the solar wind, which we will get back to in detail because that has surprisingly been one of the most actively researched areas in this field in the last couple of years. Not without us expecting it, but it turned out that this is indeed one of the painful points that we may have underestimated originally, and where we're now realizing we need more information on that in order to improve our data to the point that we can detect gravitational waves. So anyway, this is a realistic data set that shows some of these interesting behaviors. The unmodeled effects that constitute the residuals, obviously there's Gaussian measurement error, which you cannot do anything about other than building a bigger telescope, getting longer observations, getting larger observing bandwidths. And so all of that is happening, but the data from the past is, of course, it has the errors that it has. Pulsar erratic behavior, which we call timing noise. These are instabilities in the pulsar rotation. They mostly affect the slow pulsars that we don't use, but increasingly we are getting sensitive enough to see that millisecond pulsars do show this phenomenon as well. And so that, again, is a challenge, mostly because it's a stochastic process, and so we cannot really model it. We can only try and correct for it afterwards. Gravitational waves, obviously, they're one of the things that should be in the residuals here, and that's the trick to dig those out. Interstellar propagation, I mentioned that dispersion term that's dependent on the electron density. And so increasingly we're discovering that is one of the things that we really want to try and correct for. And of course, the solar wind, which I mentioned here, that's part of that. And in fact, you can see even before, because those purple and white points, I think they're from the French Nénuphar telescope. It's a variation on the theme of the LOFAR telescope. So it's a very recent, very low frequency telescope. And that, because it's such low frequency, you can see these things very well. Before the Nénuphar era, you still see these points spreading out about every year, but to a lesser degree. And that's because these observations are at higher frequencies, so you cannot see the signal as well, so you cannot correct for it as well. And so that's one of the things that we try to do, getting extra low frequencies to get a better handle on those signals so that even the higher frequency data can be corrected for. Now, as we're digging out all these unmodeled effects to try and improve the residuals so that we get more sensitivity to gravitational waves, there's basically two fundamental tools that we can use. There's spectral properties of the signals of the residuals, and there's correlations between the residuals of different pulsars. Spectral signatures, basically we distinguish typically between two types of noise in the residuals. There's white noise, which is typically Gaussian measurement error or random errors that just happen as we make our observations. And there's what we call red noise, which is low frequency noise. In the right-hand plot here, we have on the top an extreme example of a pulsar that shows this red signal, this low frequency noise. In this case, you could say it looks a bit parabolic, so you could fit for period and period derivative, and that would improve things, but you can also see there's clear deviations from parabola. So even if you were to do that, it would not flatten out. It would not become white. It would still have significant structure. And so that's typical of that red noise. On the bottom here, we have the power spectrum, and I suspect this is Lomb-Scargill periodogram, where you see the clear white noise floor on the right at the highest frequencies. As you go towards lower frequencies, these power levels start spiking up until they max out at the lowest frequencies you're sensitive to. There's basically three potential sources for red noise. So if we see residuals that have red noise, it's typically one of these three that cause it. There's timing noise, so intrinsic instabilities, which I just mentioned. There's interstellar medium variations, because the electron density is not just randomly Gaussianly distributed. The electron density is actually part of a turbulent cascade in the ISM. And as a consequence, the distribution of electron density scale sizes is also a red power spectrum. It is dominant. There's more energy in the electron distribution at low frequencies than at high frequencies. And as a consequence, these time series of interstellar dispersion, they also have a red noise spectrum. So that's one of those red noise things. And then the gravitational wave background, which is a background consistent of supermassive binary black holes, which emit gravitational waves. Those gravitational waves affect us, and I'll get into how that works in a moment. And due to the variation in orbital periods of these supermassive black hole binaries and the distribution of these objects in space, and therefore their distribution in amplitude, we expect that signal also to add up to a red noise spectrum, so that the lowest frequency sources, there's most of them, and therefore they add up to the most power. At higher frequencies, there's fewer of them, they're further away, and so they add less power. And so you end up with this typical low frequency power spectrum. So those are typically the three red noise spectrum, and those effectively fight against each other, because once you have red noise, once you have one type of red noise, it's very difficult to fight against the other types of red noise. One thing that can help in that is correlations, and specifically, well, timing noise is obviously a pulsar-specific property. That means if you have red noise that does not correlate, that would be timing noise, so you can model that and subtract it in principle. A gravitational wave background, as we'll show in a moment, would also be correlated, but in a different way. Would be correlated between pulsars, and so that's the main difference there. Two other phenomena that could be red, but not necessarily, but that are correlated between pulsars are errors in the clocks. So if your time standard is off, then it's off for all pulsars equally, and therefore that it would be a monopolar correlated signal where every pulsar shows the same mistake. And so that in that case, the timing residuals would be positively correlated for each pair of pulsars that you correlate. Solar system ephemeris errors, that means if we don't know the position of the Earth at the time of the observation, and the Earth is actually moving around a different spot in the solar system than we expect, then half of the sky would be pulses would arrive earlier than we expect. The other half of the sky pulses would arrive later than we expect. And so you get a dipolar correlation in your timing residuals. And so by looking at the spectrum, looking at the correlations between pulsars, we can try to take apart, analyze that noise, and basically distribute the power into these different buckets, so that ultimately we can mitigate the other errors, the other effects, and remain with the gravitational wave background. That's the name of the game. Yeah, this just summarizes what I just said. Clock drift would provide monopolar correlations between pulsars. Solar system ephemeris errors, so that means an error in the mass or position of solar system bodies, because they all affect the location of Earth, obviously, would provide a dipolar signal. I say to first order because, of course, this also changes in time and the direction of the dipole moves around. And so it's a little bit more complex than just a plain dipole, but fundamentally it comes down to that. And then gravitational waves, the ultimate signal that we're aiming for, are obviously quadrupolar correlated. I believe you all have a pretty good background in gravity, so I probably don't need to explain this in great detail, but just to give the sort of hand-wavy argument, why are gravitational waves, why do they introduce quadrupolar signals in our pulsar data? If you consider a ring of pulsars and the Earth is in the middle, we're observing the arrival times of all of these. You can imagine that is the same as sort of measuring the distance to the pulsar, because as the pulsar gets further away, your arrival time gets delayed. And if you now pass a gravitational wave perpendicular through the screen, it will deform space in this quadrupolar way. And so at any point in time, you can see that the effect of the gravitational wave on two pulsars that are close together in the sky is identical, basically, or very closely related. So that's positively correlated. Pulsars that are on opposite parts of the sky, for example, one at the top and one at the bottom, they again would do the same thing at the same time. So that's again positively correlated. And pulsars that are at 90 degrees, they would be anti-correlated. And so that's what gives us that quadrupolar signal. Effectively, this is another animation that shows that if you take pulsars pairwise and you correlate their timing residuals, if there's no gravitational waves, you basically expect no correlation as a function of the angle, unless your clocks or your solar system ephemeris are on. If you have gravitational waves, you do get correlations for pulsars that are close together. You get anti-correlations for pulsars that are 90 degrees apart. And you get positive correlations, again, for pulsars that are on opposite sides of the sky. And so that's what gets you your quadrupolar correlation. And that's the signal that we're really looking for. In practice, of course, we're not just working in 2 dimensions. We have a pulsar constellation spread in the galaxy. This is sort of an artist's impression of the nanograv array, which since then has actually again grown. And so there's more pulsars. And so as the gravitational waves go through, all these arms of this detector network get stretched and squeezed And it's that really that effect that we're looking for. Again, as said, this is an artist's impression. The choice of which lines to draw and which not is quite arbitrary, but it gives you an idea of this galaxy-sized detector, really, because the distances of these objects here are accurate. So they are really spread out through a fair portion of the galaxy. Right, so to summarize, we have lots of pulsars. We time them to the best of our abilities, try to improve the timing model to the extent that the timing residuals, the unexplained parts of the arrival times, get minimized, get optimized, become as sensitive as possible to this quadrupolar correlated red noise. How can we improve the system? Sort of what is our sensitivity for the gravitational waves? What is it dependent on? The most useful equation for predicting our sensitivity, so our theoretical sensitivity, dates back to 2013. And it's basically, it comes down to this. It's a fairly simple relationship where the number of pulsars is the foremost property of importance. And that's mostly because, of course, the number of correlation pairs that you find is highly dependent on the number of pulsars. And that is really what allows you to probe that quadrupolar correlation curve. The second most important term is the time span of your data. And so the longer you're at this game, the more sensitive you are, and the better you can measure these correlations. Next one, the amplitude of the gravitational waves. Obviously, the stronger the waves, the easier it is to detect them, but that's not really a design property of our array, so I'll skip over that. Sigma is the precision of your TOA measurements. In fact, it's the RMS, the root mean square of your timing residuals, and obviously, the more precise that is, the more sensitive you are. Although in reality, it's a little bit more complex than that because of these frequency-dependent effects, where lower frequency data may not have as good TOA precision, but it may give you a very good lever arm on your propagation effects, which can then improve the higher frequency data. And so data is also complementary in a way. And so that's why sigma is a bit of an oversimplification. And then finally, capital C, that's the weakest parameter. It does not depend massively on that, but it does contribute. It's the cadence of the observations. So you observe once a month, once every 2 weeks, etc. So as many observations as possible does gain you sensitivity, but not quite as much as having more pulsars. Now, the bottom line of this really is increasing your number of pulsars, increasing your cadence, so your number of observations, increasing your timing length at some level, and in fact, increasing your sky coverage, which is not taken in here because this basically assumes sort of a homogeneous distribution of pulsars on the sky. Basically, what you need is you cannot do this with one telescope. With one telescope, you can get a lot of observing time if you're lucky. You can do really precise timing on many pulsars, but you're always limited at least to the portion of the sky that you can see, but typically also the amount of observing time you can get, and in fact, the frequency ranges that you have access to. So the most obvious way of boosting your sensitivity by a factor of a few is by collaborating internationally. And so that is what has been happening over the last 2 decades. This whole game, the theoretical basics of the fact that this should be possible were already posited in 1989, 1990. And so the idea has been out there. But back in those days, we barely knew any millisecond pulsars. So these really rapidly spinning, precisely timed pulsars, back in 1989, we only knew, I think, 3 of those. So you can't make a pulsar timing array with just 3 pulsars. So the concept was there, but it wasn't practical yet. In the mid-90s, there was a couple of very successful campaigns, primarily in the Southern Hemisphere, that discovered a lot of new millisecond pulsars, and people started timing them, started improving the timing. And by the turn of the century, it started to look like maybe this thing could work. Then at that same time, the turn of the century, sort of 2001, 2002, there was an insanely sensitive and insanely successful pulsar survey carried out at the Parkes Radio Telescope in Australia, where the total number of pulsars known in the galaxy got doubled in a matter of a few years. As you may know, the first pulsar was discovered in 1968. So the field at that point was already more than 30 years old, 30 years of pulsar surveys, pulsar discoveries, and yet in a span of a few years at the turn of the century, that number got doubled. So at that point, People in Parkes were excited. They were highly successful. They were sort of the center of the pulsar universe. They said, well, why don't we try the next big thing? And that's when they started pulsar timing arrays. That was in 2004. They started in 2004. They sort of got the preliminary work done, got some initial results. And that's when the other pulsar astronomers in the world started paying attention and saying, hey, they're onto something. This is something really interesting and really nice, and we should get onto that as well. And so in short succession, back in the early 2000s, both the North Americans, led by the US, but with close collaboration from Canada primarily, they started the nanograph pulsar timing array and a consortium of European telescopes, originally 5 of them, although Sardinia was not built yet at the time, but there were plans, and so they were already involved in the collaboration before they even had a telescope. Eventually, LOFAR got added. So a consortium of European telescopes got together to form the European pulsar timing array. And these 3 traditional arrays, the Parkes pulsar timing array in Australia, nanograph in North America, and EPTA in Europe, they got together after a few years. I think 2007, 2008, they really got serious about binding this all together into a global collaboration. As time progressed, India, primarily with the GMRT and hopefully soon with the UTI telescope as well, they also joined, I think around 2020. So it took them a bit longer to get to that point, but they've also joined now. And as the Meerkat array in South Africa, sort of the first next generation telescope really got commissioned and started observing, the African Pulsar Timing Consortium also joined just recently. I think formally they joined last year. So these 5 pulsar timing arrays now, they all work together in the International Pulsar Timing Array Consortium, which I'm supposed to manage. It's a bit like herding chickens occasionally, I must admit, but it's a really interesting group, really nice group of people, and it's just fascinating to see all of these data from all these telescopes come together, which again causes challenges, but it also means that we can do things much better and much more sensitive. I also have the CPTA with the fast radio telescope, the next generation telescope in here. The reason is that while they're not official members of the IPTA, they do collaborate with us, and we have a memorandum of understanding, a collaborative agreement to work on the next data release. And I'll talk more about that in a bit. But so there's increasing collaboration with the Chinese as well to try and work together rather than against each other. So that's all good and that's all well, and we're going in the right direction. Now, how close are we? As I mentioned, this project started basically in 2004, so we've been at it for 22 years. The claim has always been we should be able to do this in 5 to 10 years. We better have something to show for it at this point. And yes, we do. So the first publication that came with actually robust evidence, if you like, to indicate that, hey, there is something here, and we can't say what it is. We can't say it's gravitational waves, but if we were to get close to gravitational wave detection, this is what it would look like. So that's not the same as saying what we see is a gravitational wave. It is the same as saying if we were to see gravitational wave, this is what it would look like. So that was in 2020 when Nanograph showed that there was a red noise process, a low frequency process that affected maybe all, but definitely most of their pulsars, and that seemed to have a common origin. So you have the same signal basically in all of these pulsars. There was no correlations, so they couldn't correlate yet, but they could see that that signal looks very similar. The reason you can see a similar signal without correlation is basically a signal to noise, a sensitivity issue. If you have a correlated signal, you would first see the signal before the correlations would be significant. That's sort of the bottom line. And this plot just shows what that looked like in terms of Bayesian analysis, sort of model comparison, because all of these gravitational wave analyses these days, all of these gravitational wave analyses these days basically are built on a Bayesian, on a basis of Bayesian analysis, and Bayesian analysis is essentially model comparison. And so they compared, they analyzed the data set and they compared a model where the red noise, the low frequency noise, was due to a common origin, a common process between the pulsars. And in that case, you could constrain the amplitude of the red noise really well. An alternative model said, okay, let's assume this is a gravitational wave background and that all of these pulsars are affected by gravitational wave background. You see a slight peak at the same amplitude, but on the whole, it's unconstrained. And so that shows, just in the model comparison, yes, there is a common signal. No, we cannot say if it's correlated yet, although it may well be, right? The peak is still there. Now, I'm going to skip a little bit forward. I will tell the story chronologically, but I'll skip a bit forward just to illustrate what this common red noise really means. This was a paper from 3 years later when they actually did say, okay, now we do see correlations. There's something there. It's still not significant enough to really be confident that it's gravitational waves, but we see a beginning of correlations, and so that there's more there. And so this was that plot that they put out at that time. Now, what we're looking at here is the amplitude of the red signal in the data and the spectral index of the red signal in the data. And so for each pulsar, they have a contour, which is, I think, the 1 sigma contour plot of the model that describes the red noise in that pulsar best. And so you've got black pulsars and gray pulsars. The black pulsars are the ones that have excess red noise, where the red noise is more powerful than this supposedly common signal. The gray contours, those are pulsars where, as soon as you use the blue model, and so in blue here we have a proposed gravitational wave background that could explain some of the red noise. So if you assume this gravitational wave background is there, then for these gray pulsars, the red noise basically disappears from your data. You can explain all of the red noise in these pulsar datasets just with this one gravitational wave background that is common to all of them. So that's why I said all or most pulsars. It's quite possible that this signal is in the black pulsars as well. It's just there's additional signal in there which, well, hides most likely the common signal that's there. So this is what we're looking at, really. Although, again, this is 3 years later, so there was more data, was more sensitivity, and that's why you could make this nice plot to demonstrate this very nicely. Back in 2020, we were not quite at that level yet. All we knew was there is red noise, and it seems to be similar between more than half of our pulsars. Now, when Nanograph came out with this work in late 2020, the other PTAs immediately jumped and said, hey, we saw that too. We just, didn't believe it or whatever, or we were checking our details, whatever. So they all got a bit stressed about this. And within a year, basically the other PTAs, the EPTA and the PPTA, they came out with their own analyses, similar to the Nanograph analysis, but based on their own data. And this was what came out there. So this plot in the bottom right corner, it shows basically, well, these are the publication references. That's chronological. On the x-axis, it's got the amplitude of the gravitational waves or of the red signal on the y-axis. And so all of these open markers here at the start, those were all upper limits, where since 2006, basically, when the first limit came out from Parkes, up until 2018, when the last limit was published by Nanograph, for those 12 years, all we've done is said, if there are gravitational waves, they can't be this bright because we would have seen them. And so we had a gradual slope down and sort of a flattening off, which again is an indication that we're getting close to something. And then the closed markers here, those are amplitude estimates of this common red signal. So again, there's not necessarily gravitational waves, it's a common red signal. Now, you can immediately see that there's a little bit of a problem here in that all of these amplitude estimates are, well, marginally consistent in some cases, but on the whole, larger than some of the best upper limits that we've had to date. And in fact, this best limit by the Parkes pulsar-timing array back in 2015, when Parkes came out with their red noise paper, where they basically show, hey, we have a signal that is much more powerful than the limit that we placed only a few years ago. They actually do admit that there was a mistake here and that this limit should have actually been a factor of 2 or 3 higher. That still does not quite explain the discrepancy. And so they're actually suggesting that maybe this gravitational wave is not stationary. Maybe this gravitational waves got stronger over time. There's a little bit of a contentious argument. Not everyone buys that, but time will tell. And either way, the tension between the very constraining upper limits and the much more powerful red noise signals is something that does need to be resolved. Now, once everyone had come out with their common red noise, the next question really became, is this real? Like, can this really be a common signal like a gravitational wave background, or is there another possible reason? Is there something else that could have caused us to get this result? even though there wasn't necessarily a gravitational wave. And so two main studies were done there that came with very interesting results. The first one was by the Australians, Goncharov et al. 2021. And they showed this picture where, again, you have the amplitude of the red signal on the y-axis, the spectral index on the x-axis, and the crosses indicate random red noise signals that they inserted in their simulated data. So they did not have an underlying uniform process that affected all the pulsars equally. They had different processes with different with different parameters that affected each data set separately. And then they ran the standard analysis like all the other PTAs had done. And what comes out is the blue contours, where the Bayesian analysis basically prefers a model that says these are all the same process, and these are properties of the process, and that can explain everything you see. The conclusion there was that even if it's not a common process, even if it's not just one gravitational wave background that impacts everything, it could be different things like timing noise, for example, that are just happen to be in a similar amplitude range. And your analysis may well, if you're not careful, mistake this and say, hey, it is common, when in reality it isn't. That doesn't mean that this is what's happening. It could still be that there's an underlying common signal. They're basically just saying we need to be really careful, and really we need to find the correlations, because if there are correlations, then it's obvious that it is a common signal. Because if they're random signals, they cannot correlate. The second work was just published last year. This was from the group in Milan, in Italy, who showed that even if you don't have a common red signal, but you have a data set that's imperfect because there are some points that are off by more than they should be, and of course, due to instrumental failure, due to radio frequency interference, due to a number of issues, this is a very realistic scenario. They showed that if you have a significant number of outlier data points in your timing residuals, you could artificially create the same result. You could find that, hey, there's a common signal because there's a certain property of the data that seems similar, even if the origin is completely arbitrary. And so basically the takeaway message of that work as well was we really need correlations. We can be very excited about a common red signal, but it's not the end of the game. We really need to find that the signal is correlated, ideally in a quadrupolar way. Now, it's very nice to talk about correlations and quadrupolar correlations, but looking for those is actually more challenging than we might think. This had been known for a while, even though this paper back from 2016 had been maybe not as widely distributed as it should have been. So definitely some of our colleagues were not aware of this. At this point, I think everyone knows. This is Tiburzi. She was an Italian PhD student at the time, working with the Parkes pulsar-timing array again back in 2016. And what she did, she looked at various signals that could or could not correlate. So she looked at the gravitational wave background, obviously. This was just random timing noise. This is clock errors, solar system ephemeris errors, a very particular clock error, a very particular example of solar system ephemeris. These are instrumental errors where a certain subset of your data is affected by some error that the rest of the data is not. These are stronger instrumental errors. And in fact, here, as you can see already, she's got 3 different types of effects where 3 or 4 different subsets of the data have different errors. And then here at the bottom, you have the solar wind. So what she looked at, she simulated each of these different types of effects, and then figured out what the correlations of those signals would be as a function of the angle on the sky. And so here in the top right is the textbook example of the gravitational wave background. This is the quadrupolar correlation. Now, the tricky thing here is that in the right column, she shows the average of 1,000 different simulations, which means that all of the noise gets averaged out and really only the signal remains. In the left-hand column, she shows one realization. That means this is what a realistic universe would really look like. And at that point, you can see the gravitational wave background looks a lot less convincing and starts to look a lot more like some of the other correlations. The final thing is the sampling in the x direction. That is, of course, related to the position of your pulsars on the sky. And as mentioned earlier, this is why we want as many pulsars as possible. Because a random distribution of pulsars on the sky, well, they're never really random, because pulsars are primarily in the plane of the galaxy, which is only one plane to begin with. And and they are primarily towards the southern hemisphere, towards the inner galaxy. So the spatial distribution is highly inhomogeneous, it's highly concentrated, and as a consequence, our sampling of these angular separations is also very much biased by the shorter separations and the larger separations, which is really where the quadrupole shows its unique feature. Those tend to be very poorly sampled. As a consequence, they showed in this work that it's extremely tricky to differentiate between these different types of correlated signals. This is another plot from that same work where on the x-axis you sort of have a range of different, on the x-axis is the amplitude of the gravitational wave background. And so these Gaussians here are different models that predict the amplitudes that we'd expect. And these points here on vertically above those distributions, those show at what amplitude your correlation analysis would get confused by clock errors, solar system ephemeris errors, instrumental errors, and the solar wind. The full symbols here are realistic simulations of what such errors could look like and what impact that could have. And so a clock error, similar to the difference between the International Atomic Time and the BIPM clock standard of 2013, would get you a correlated signal that could be mistaken with a gravitational wave background at about this amplitude, which is roughly where we see our signal. Now, luckily, this is a signal that we can correct for, and if you correct for it, that effect gets reduced, which means the clock errors may not be a big issue as long as we deal with them. The ephemeris errors, similarly, the solar wind is the primary concern here. That is the signal that could easily be correlated, and where the corrections in 2016 are probably insufficient. If we expect a gravitational wave around here, and the reason this area is shaded gray is because, of course, in 2015, the Parkes pulsar-timing array put its limit, its best limit ever, at 10 to the minus 15. So back then, when that was the best limit, that we basically expected gravitational waves to be lower than that value. That's why that left area was shaded gray. That was where we expected gravitational waves to be. And so the solar wind, even if you correct for it, gets right there at the edge. So based on this work, we knew not only we need to look for correlations, but also we need to look for all of these correlations and try to correct for them. So that's what happened next. And so this is from a paper in 2020. This is an Australian author, but it's actually using the entire IPTA global dataset, and it shows how different errors in the clocks can be reconstructed, and actually shows that it works really well. It can reproduce some corrections that the clock community created, and it reproduces them really nicely. So we think we have the clock corrections correct. This is a similar experiment based on the solar system ephemeris, where the green and the yellow markers indicate the uncertainties of the mass measurements of the different planets based on the JPL solar system ephemeris, and the black line basically shows our sensitivity based on our pulsar timing, which initially came very close, but then JPL improved their uncertainties, and so now we're relatively far off, except maybe for Jupiter. So again, we know that the uncertainties in the model are below our sensitivity at this point, so we are confident that the solar system ephemeris are not causing us harm. In the stellar propagation effects, these are a few plots of LOFAR data where we have significant variations in interstellar propagation. And the nice thing is, because of these low frequency data, we can measure this extremely precisely, and therefore we can correct the higher frequency data for it. Same story for the solar wind. Here, all of these spikes are solar wind. You can see this is variable in time. You've got the solar cycle, but also you have a lot of variation in the solar wind, which we are now starting to deal with, and so to try and correct that precisely. And again, this is maybe one of the areas of most actively being researched right now, especially because it can introduce correlations that are spurious. Yes, more scary stuff. There are theories that show that interstellar propagation is, of course, frequency dependent, and as a consequence, your interstellar dispersion measurements may not be able to be transferred from one frequency to another. Because we're running out of time, I'm going to skip over this, but the bottom line is the theory may be more pessimistic than it needs to be. We finally discovered this effect in observations, and it's actually much less bad than originally presented. So, notwithstanding all of the problems and challenges that we've had, we still got somewhere where we like to be. I haven't been able to get this animation to stay up on the screen for very long. Yep, there you go. But basically, this is the latest result from Nanograph published in 2023, where the yellow error bars are the measurements. And you can see there is a bit of a quadrupolar phenomenon there. It's not quite as extreme, it's as clear as you might want it to be. And so that's why we haven't called this a detection yet. It's at a 3 to 4 sigma level. The community has has converged on a community standard of 5 sigma before we actually call it a detection. That's why right now we say we've got clear evidence for a correlation, for a gravitational wave, but it's not significant enough yet to really be a detection. Nanograph came out in 2023, but this was actually a coordinated effort where all of the PTAs didn't yet work together, but synchronized their analysis. Because once in 2020, we knew there was something, we knew we had to all go and see if we could find the correlations. And so the EPTA collaborating with the Indian PTA, Nanograph and the PPTA, they all independently did their own analyses simultaneously, and then came out together with their independent results. And so this was the bottom line of that. This is the amplitude of the quadrupole correlated signal. This is the spectral index of the quadrupole correlated signal. And the European and the Australian PTAs, they only just touch at the 1 sigma level, but the Nanograph is right on top of that touching point. So basically, they're all extremely consistent. It's a very nice result to see that even though the data are all different, the analysis methods to a large degree are different, they still agree extremely well. Again, though, all 3 of these are basically 3 to 4 sigma. We don't have the 5 sigma result yet. This is that same plot as earlier, but now the x-axis is actually time. And here on the right, you have the 4, because the Chinese actually joined right at the end as well. We have the 4 measurements of the amplitude of this quadrupole correlated signal. And I've indicated in blue here the range of amplitudes that have been published here from this correlation analysis. And again, alarmingly, you see it's larger than the best upper limits, except for the EPTA. That's the only ones that are sort of on the edge. Nanograph, IPTA, and Pikes, they're all well below that level. And in fact, even the correlated red noise in many cases is actually at a lower level than the correlated signal we now see. There's significant error bars, so this is not necessarily a problem, but it is something we need to be aware of. This is that same plot, but a bit blown up. And so the brown here, as mentioned, the Chinese, they joined this really late. They said, oh, actually, we also have a result. Can we get it out at the same moment? And they did. But their analysis was very different. And so it's very difficult to translate their numeric results into the same framework that we use. And that's why the error bars look really weird. But also they have the shortest data set, of course. They did this with the FAST telescope. It's only been active for a few years. And so they only have a few years of data, which for a low frequency signal is, of course, not very constraining. But yeah, those are the results as of 2023. As mentioned, it was the coordinated effort, and so we had 18 papers all coming out at the same moment on the 28th of June, 2023. What was very stressful to get this all organized, but we're very happy that it worked. About half a year later, Meerkat also came out with their result, which again is consistent with everything, but they didn't manage that 28th of June deadline, so that took a bit longer. And now we saw that everyone sees the correlations. We're all just below the 5 sigma level. We decided to do the next obvious thing, that is to pull it all together and to make one joint global analysis. And so that's the full IPTA combination, which we call DR3, the 3rd IPTA data release. And that's coming up now within the next half year to a year. Yes, in fact, in my abstract, I think I promised I would go into the sources of the gravitational waves. As I was preparing my talk, I realized that I have enough details to talk about that. I don't have a lot of time for the sources, and you probably know more about that than me already. So I've kept it fairly short. And as I'm looking at the clock, I realize that I'll have to go really quick on this. But basically, the signal that has been seen so far, which again is not a detection, but it's getting very close, is consistent with astrophysically motivated gravitational wave background. That means with the population of supermassive binary black holes. But only barely. You do need to tune your models a bit. For example, you need to have more eccentric binaries, or you need to evolve them more rapidly, which means you need more gas accretion. And so you can make it work, but the standard supermassive binary black hole population models that we have don't really match because they actually expect a lower amplitude, which again is interesting because the previous results we had, they actually had a slightly lower amplitude. And so that discrepancy it's very interesting also from an astrophysical perspective. Some early universe models do fit better, but again, the standard inflation models don't actually work all that well. I've put some references here so you can look at this at your leisure. And again, I stress poor evidence still. The significance of these results is still very limited. So it's very early days, and we really need to wait for that more comprehensive, larger analysis to really get somewhere. A very brief word on single sources. We always have worked towards a gravitational wave background detection. We've always talked about red noise, etc. Single sources could also be detected. And in fact, here is the blue curve is the predicted sensitivity curve for the IPTA last year. So that's basically the combination we're working on now. The dots are simulations of what kind of population of gravitational, of supermassive binary black holes we might get. As you can see that there's, according to this simulation, there's several that are popping up above our sensitivity level. So there's reason to be optimistic. This is a similar type of simulation by Alberto Sassana from Milan again, where you see, the red line is gravitational wave background. And so we ultimately hope to get sensitivity to those lowest frequencies, but you could get single sources that stand out significantly so that we might actually get those as well. And really important for this plot is it shows you the kind of frequency resolution we get. And that is, of course, related to how long we've been observing. So the longer our observing spans, the higher a resolution and the more likely that one of these sources is going to stand up out above the background. So that's also why single source detection is becoming a much hotter topic in PTAs right now than it used to be, partly because we're getting close to detection and therefore the chance of a single source detection gets larger, but also because our baselines become so long that our resolution becomes very high, and therefore, again, we continuously increase our sensitivity to single sources. I wanted to finish with two more comments on the upcoming data release. Now we have 6 PTAs that all work together for this data release. This is a Venn diagram that shows how many pulsars are in common between the different PTAs. It does not show all of them because it's impossible to show such a Venn diagram with 6 different groups and all of their different overlappings. So it's actually a lot more complex than this. But just to show there's a lot of work, there's a lot of data, there's a lot of pulsars, and this is also why it takes a long time to do this analysis. The next thing, I want to briefly acknowledge the recent publication by you and Alan, that's Bruce Allen from the Albert Einstein Institute in Hanover, who have submitted last December a paper where they said, well, you guys published all these limits here, all these marginal detections here back in 2023. You guys are trying to put those data together in a very nice and perfect way, but I can just throw them together quickly and easily, assuming everything is fine. And then I can get a combined measurement, actually, which is, as it turns out, not quite as sensitive as the individual data sets, but it is a lot faster. Here again, on the x-axis, I've actually put time rather than references. So you can see, since these publications in the middle of 2023, we've now gone 3 years effectively without any publication. That is not unprecedented. It happened right in the early days of PTAs as well. But basically, since 2011, we've never had a 3-year gap. That means it's taken us a lot of time to get anything done. You could draw your own conclusions from what that means. But really, if you want to believe me, the reason we have that big gap is because the data sets are getting bigger, more complex, with more partners, more telescopes, and that just makes the analysis much more difficult. You and Alan tried to avoid that complexity by making a simplistic analysis, a simplistic combination that can be really, really fast. But the jury's still out as to whether that actually gains you any benefits, because you don't, in that kind of combination like they submitted, you don't actually make use of the complementarity between the different data sets. And I think the complementarity is really the strength of your work. In fact, I should have put the archive reference because I say submitted, it's actually on the archive. I can get you the reference if you like, but you can probably just find it. There's not that many papers with this author setup. I also added here in pink, I mentioned it earlier, the Meerkat result came, in fact, it was more than half a year. It was more like a year and a bit. Their data release was half a year later, but it took them a bit to get the gravitational waves as well. And so they, again, have a result that's very consistent with the others. It's, again, 3 sigma or thereabouts. It's about the same amplitude range. So everything is consistent. We're now working on the combination, which is a lot of work. But we do expect at this point to get that done by the end of the year. The data combination is basically done. We're still finalizing a few things, but mostly it's there. The gravitational wave analysis has just started. And so I don't really know what's going to come out of that yet because we haven't got the results yet. But I am optimistic that given that all of these individual data sets had 3 to 4 sigma, previous work has shown that by doing a coherent combination internationally, you get another boost of a factor of 2 or 3 at least. So I do expect that we can get that 5 sigma actual gravitational wave detection and then move into gravitational wave astrophysics by the end of this year or early next year. So that took me exactly an hour. So thank you for your attention, and I hope you enjoyed this. If there's any questions, I'd be more than happy to take them at this point.
Thank you, Joris, for this really nice talk. Are there any questions?
This is Kim Wang. Yeah, I would like to ask a question about your conclusion that the third point may soon detect individual supermassive black hole binary or a background. For a single source, there should be some something like the dipole anisotropy, but so far there's no detection on this anisotropy. So does it mean there is likely a background, isotropic background?
It's a good question, and the answer is we don't really know. So we don't really look at the models at that point because we don't want to be biased. We just look at what's in our data, and the risk or the challenge really is all of the complexities I've talked about, because we have in the past had people come up and say, hey, we detected a single source at this frequency, and then you go look at it and you go, well, maybe there's some astrometric parameters you should have fitted for. And so we've had a few false detections internally, which has made us very careful. And so that's why right now we have within the IPTA, there's a committee set up specifically to address issues like this. If we detect a single source, or if we think we do, how do we go about making sure that this is the real thing and that it's not just some artifact? Because you're right, it's very difficult to do that. And when we do, the astrophysical implications are obvious. So we do need to make sure that we do that right. Okay, and so right now, we don't have evidence for a single source. It's just people are optimistic. But then people are always optimistic. So maybe you shouldn't read too much into that. And in fact, maybe a second aspect to that question is, I say we don't look at models. What we do look at is if there are papers that come out and that study individual objects, results of binary mergers, or sort of these X-shaped AGN, etc. There have been papers where they sort of suggest, hey, there must be a supermassive binary black hole in there. I think the most legendary is 3C66b, which back in, I don't remember, 2001 or thereabouts, I think Sudo et al., a group from Japan, looked at the X-ray variability, and they derived a supermassive binary black hole model for that binary, which it's plotted here. It's got an insanely high amplitude. In fact, the reason it has such a high amplitude is because it's an upper limit. So it could be anywhere below there, and likely it is much below. But so predictions like that, where there's an actual prediction saying there might be a binary supermassive black hole in that area at that frequency with this amplitude, those are things that we definitely do want to test and do look out for. But so far, I don't think there's any that are actually detectable. 3C66b, we've constrained the models, that it's not there. I think there's OJ221 or something like that. There's another one that we're getting close to the prediction, but we don't have it yet.
I say in the other word, okay. I believe the almost 5 sigma is gravitational wave. I believe that. And how, if a single source, then there should be very large anisotropy in the data, but we don't observe any anisotropy yet. So it kind of hard to believe. We have 5 sigma detection of gravitational wave, if that's true, and we don't detect anisotropy, that means it's not a single source. Am I correct?
Correct. Yes. That's also why you're right. There's two angles of attack for the single sources, really. You can look at specific frequency bins and look whether at those frequencies you have a polar correlation, or you can look at your sky map of sensitivity and see if you can find anisotropy in whatever red correlated signal you have. Both of those approaches are being taken. The anisotropy results, yeah, they're inconclusive at this point. You're right. We don't see anisotropy. But I think, and this, you're right, this is not my strength so much. But I think the difference there is also in the isolation of the frequency. And the 5 sigma result you mentioned, that is really, well, it's not 5 sigma yet. Let's be clear about that. I do hope we get there within half a year, but we're not there yet. But the correlated signal here that I've been presenting, that is really assuming a uniform background model. That is assuming there's no anisotropy. It's assuming there's no single sources. And under those assumptions, we get that 3 to 4 sigma result. And that really relates to the power spectrum where you have that red slope. A single source detection would not look like this at all. That would just be a single bin that has excess power. And, maybe you could argue there's a few bins here that might stand out a bit. And so that's the statistical analysis that you need to do. Does this stand out sufficiently? And is excess power, is that correlated or not? And so it's a very different analysis. The anisotropy searches as well, I don't think they isolate individual frequencies. And so they really look more, is there potentially superposition of 3 or 4 individual binaries that are dominating our red noise signal, which could also be because our frequency resolution is not particularly great. But so I think the analysis and the way it impacts our data between an actual single source that's at one frequency or a background or an anisotropic background that's dominated by a few single sources, I think they're very different analyses and they would affect your data very differently. Does that make sense?
Okay.
Or am I still not answering your question?
Interesting. Yeah. Okay. Interesting. Yes. It's much more complicated than I thought.
Yes.
Yeah. Thank you. Yeah.
There's in fact, I think, Sarah Burks-Pollauer of West Virginia University published a review paper on sources a few years ago, which also goes into single sources a fair bit. She's actually chairing the single source working group or committee that I just mentioned. And Steve Taylor from Vanderbilt University in Tennessee, he put out a long review not so long ago, which goes into a lot of this as well. He's one of the key players in this anisotropy search type thing as well. So I very warmly recommend those 2 references to you if you want to look into those aspects more. But you're right, it's quite more complex than we initially assumed.
Okay, thank you. Thank you for the information.
Okay, are there other questions? Yes, Daniel?
Hello. Might be a naive question, but in this plot that you're showing, the spectral index seems to be centered at around 3.3. But as I understand, when we do like the Hellings and Downs thing, we assume like something like 4.3 for the index, right? Like how does that what's the word? How is that consistent?
Right. That's not consistent. That's a very good point, and I'm glad you brought it up. If you look at these papers, they actually always do 2 things. One thing that's what's shown here is they say, looking at the data, what is the spectral index and what is the amplitude? And in that, when we do that, we actually almost consistently, because you can see the blue curves the green curves, which is the PPTA, they actually get somewhat steeper spectra. The EPTA gets much flatter spectra. So the spectral index is not very well constrained at this point, but we very often see that the spectral index we get from our data is not consistent with what the predictions are for a background based on supermassive binary black holes. And so this is one of the reasons that there's actually alternative models that predict or that can explain this better than the astrophysical background of supermassive binary black holes. The other thing that they do is they say, if we assume the spectral index is what the GW, what the supermassive black holes predict, what kind of amplitude do we get out? And so you have both analyses, but in both cases, actually, you're right that it's not it's definitely not spot on the prediction. The predictions are not easily consistent with what we find in terms of spectral index. And at this point, we don't know why. I hope that within the next year, as we get more sensitive analyses, that we can constrain this better and that we can see where that moves. Like, does the spectral index move towards the value we expect, or does it actually stay offset? And then it becomes a question for the astrophysicists, the galaxy evolution people. Can you reproduce this somehow? And so that is really, the question that we'll end up with. So this plot, I went over it very quickly, but it's one of these traditional plots that Alberto Susana has made throughout his career, where the strength of the gravitational wave basically is on the y-axis and the frequency is on the x-axis. Each point here is an individual supermassive black hole binary. I think he bases this kind of results on the Millennium Run, or the results that they got from that. And so if you add up all of these sources, you get the red line. And so that's how you get your gravitational wave background. Now, you can change the slope of this if you change the distribution of your supermassive binary black holes. So if we do find a slope that is different from the prediction that you mentioned, it may mean that the source is different, that it's not supermassive binary black holes. But it might also mean that the supermassive black holes are distributed differently than we thought, because galaxy evolution goes differently than we thought. That's a conceivable thing. And in fact, more recent work, which I haven't included, maybe I should have, more recent work actually shows that there is an expectation that this spectrum actually tips over at some point. As you go to lower frequencies, it tips over and it becomes flatter at some point. And so maybe that tipping over point just needs to be shifted, meaning that the redshift distribution of these supermassive binary black holes is different. And so I hope that these are the kinds of questions that we'll dig into in the next couple of years, and that we'll actually get clarity on, because right now it's all very confused. And I think that's partly because the results are not fully constrained yet. Does that answer your question?
Yeah, and I guess a lot more still to learn. Yeah, thank you very much.
Any other questions? If not, maybe I can ask 2 questions, or let's start with one. You mentioned that there could be also other sources. I mean, right now I think you assume mainly binary, supermassive binary black holes, but what other sources could be there that you can detect in the pulsar-timing array?
Yes, so right now, so far, we've mainly looked at the supermassive binary black holes. Based on the 2023 results, there's been a huge outpour on the archive in literature for early universe models. So alternative theories of gravity as well, where non-standard gravitational theories come up with predictions from inflation or thereabouts to try and reproduce this. And to some degree, they're successful. Partly, I think, because the parameter space is large enough that you can tune things a little bit. But partly also maybe because, indeed, this is what we're looking at. I put the reference here. This is a review paper I wrote following the 2023 results, just to sort of summarize where we all stand. And we go into a bit more detail on the various types of sources that could be expected there. But these are the 2 main ones that we're currently looking at. The non-standard physics, early universe, and then the supermassive binary black holes. Yeah, that's mostly it. There are other signals that we could expect, but most of those would be individual sources. And so I mentioned for individual sources, we mostly expect a single supermassive binary black hole that's relatively close and therefore powerful, and that would dominate us in a given frequency bin. But there's also other effects, like, for example, the memory effect, where you have a close encounter of a supermassive black hole, of 2 supermassive black holes. And so if they pass by closely, they completely deform the space-time metric in a permanent way, which is another signal that we could detect. And in fact, interestingly, that's the kind of signal that would initially not be there and at some point would kick in and then sort of accumulate over time. So if you remember when I said that the Parkes guys at some point suggested, oh, well, the reason our limit was so good and now we're detecting a stronger signal is because it's not uniform in time. Well, a close encounter like a gravitational wave memory effect could be one explanation for that. Again, this is not a theory that many people pay a lot of attention to, but in principle, this is something that could happen and that we could possibly see. And given the inconsistencies in our measurements, I mean, you could argue the increase in amplitude over time is because we made mistakes in our analysis and we fixed them, and so we are getting more accurate, if less sensitive, apparently. But you could also indeed argue that indeed this is an effect with memory, where the signal just adds up in time. So it's another hypothetical source, but again, not one that most people look at right now.
Before I ask this question, let me ask if there are some other questions from the audience. Seems not. So my second question would actually be, is there a way to use the signal also to probe gravity, like to learn something about the gravitational theory behind?
Yes. I haven't gone into that, but you can actually, in principle, you can study the gravitational wave polarization. Because the quadrupolar correlation I showed, and in fact, I now realize that the only real picture I have of that is the one that disappears. So maybe I'll show this one instead. Okay. This quadrupolar correlation here, it's got a very well-defined shape, but that shape is dependent on the polarization of the gravitational wave. And so it will look somewhat different if the gravitational waves are differently polarized. It's also dependent on the mass of the graviton. So we normally assume the graviton is massless. If the graviton is massive, this positive correlation at the long angles actually will go up and it will become more symmetric. And so in principle, those are things that we could ultimately also constrain. Right now, however, we're very far from that. And this is something that we would hope the next generation of PTA experiments, say with things like the SKA, maybe the DSA, would be able to probe. Right now, we're not there yet. But so those, I think, are the two main ways in which we should be able to ultimately constrain gravitational wave theory itself. For the time being, and I'll put a number on there, at least for the next 5 years, the best I think we can hope for is to do astrophysics with it, mostly galaxy mergers, alternative physics, inflation, gravitational wave, polarization, graviton mass, etc. That's something I would see more on a timescale of 10 years, maybe, depending on how much the telescope building gets delayed, of course.
Thank you. Okay. Are there some other questions? Yes, Daniel?
Sorry, one final thing. I just remembered this one. So this is the thing where Tiburzi and et al. Basically did like 1,000 versions of the signal and then plotted it this way. But I also believe that the variance that will appear here, the cosmic variance, would also be model dependent, right? Like, did they consider that part?
Which model do you mean?
Like, for example, for GR, there will be a specific shape for the cosmic variance, and then for theories beyond it, it will morph in a different way.
Yes, that they did not take into consideration in this work. That's right. That complicates things even further. Yeah.
Okay. I'll read this one. Thank you.
And that raises a good point. In fact, I think in the last couple of years, I think again Bruce Allen put something out on this as well, where they look at cosmic variance and how it affects the quadrupolar shape. And you don't want to look into that too much because it will destroy your optimism, because it does make things more complex. You're right.
Okay, thank you.
Okay. Are there more questions? If not, I end the recording here. Thank you very much again, Joris, for this talk.
Thank you for having me. And I'm sorry I went over time, but